to this issue was by Duncan, who's sadly not here today because he knows a lot about these things, but it was an evening discussion about the unsafe functions, and he had great stories to tell about what he suffered through. Yeah, and eventually I thought I should maybe just read up on how it's implemented in GHC, and since there's a lot of mystery and fairy tales and false claims about I/O in Haskell, and that it's evil or dirty or unfunctional and stuff like that. And all of that is not really true, also not really false. So I'm gonna give a rough overview without lying to you, but also without going into too much detail. So in the end, you will hopefully understand what the real world is, and yeah. Yeah, the slides are available online. Just GitHub. Kuchen is my nickname. Talks is, well, Talks. Anyway, yeah, we all know that side effects are in general evil and hard to reason about and unmaintainable and unfunctional, and people have claimed that Haskell is not really a functional language because you can print, which is maybe correct, but they're also the only point of running a program. Because, well, even if your CPU heats up when it's a useless program, that's already a side effect. So I guess even in a side effect-free language, once you run it, you could communicate via the CPU temperature. So we kind of need side effects. So all the beauty of Haskell isn't really useful if you can't make anything of it. Anyway, purely functional programming is, for the lack of a better word, it's not evil, I guess. It's fairly easy to reason about, which Gabriel gave a nice talk a year ago, I think, about equational reasoning and how you can use mathematical equalities and not using a step-by-step debugger to think about things. And that works even for I/O in Haskell, not so much in languages like C or Java. It's maintainable, mostly because of the type system, immutability, and all these things. And, well, purely functional programming is functional, I guess. But it's also completely useless without side effects. Actually, there's this video about Simon Peyton-Jones, and he says, kind of, Haskell is useless without side effects, and it frequently is reposted as Simon Peyton-Jones says, Haskell is useless, ... This is what he meant. Yeah, anyway, so in the beginnings of Haskell, people were faced with this problem. They didn't really want to give up the functionalness and have, I don't know, in other functional languages like, I don't know, the Lisps, you have everything is functional, but some functions, when you run them, they also print to the terminal. So they look functional, but they really have a side effect. But Haskell wanted to remain purely functional, but of course also be somewhat useful. So they had to come up with a way to solve this dilemma between side effects and being purely functional. And of course, well, they wanted to stay maintainable, and they wanted to leverage the type system in order to keep track of side effects. Yeah, and well, this is a very old idea. Basically, what we as humans want to do is we want to write Haskell, and we want to know what a Haskell program does. And then we give that to a magic black box, which is the compiler, and the compiler just does what the program says, and we don't really care what it does. So a usual example I give here is, if the compiler has to sacrifice a goat in order to run my Haskell program, that's fine with me. Like, I'm interested in the semantics of Haskell, and the compiler can just do whatever he wants. And this is a bit what's being done in GHC as well. So Haskell as a lazy functional language is eventually compiled down to something called core or STG. And in STG, we don't really have the Haskell ideals anymore. So having side effects in STG is completely fine as long as it preserves the semantics of a Haskell program. So the idea is really just transforming a functional program into something that does what the functional program claims it does. And in STG, we wouldn't want to worry about whether this is purely functional or beautiful or any of these core ideas of functional programming. Yeah, so what are the main problems in a lazy language when we do something like this? If we have a simple program like this, we can you probably all know the desugaring of this do notation, and we have chain function calls in the end. But when you have unspecified evaluation order and evaluation multiplicity, then you don't really know, like, why should the first line here be printed before the second line? Like, these don't depend on each other. And why should we not run this 10 times? So if you calculate 2 plus 7, the result is 14 times 7. But it's also going to be 14 if you re-evaluate it all the time. It's not very efficient, but it would be valid for a Haskell compiler to do this. Whereas it would certainly be invalid to ask for a person's name 10 times. So we have to kind of keep track of the order, and we also have to make sure that things run exactly once at the right time. Yeah, but how do we introduce order when the compiler can just reorder things at will? So if we have a chain of function calls here, f of g of h, like when is this going to be evaluated? F first, and then g, and then h. So if f was a print hello, and g was print world, and then exclamation mark, like why shouldn't the compiler do the exclamation mark first when it's unspecified? So we have to carefully choose our functions in order to do that. So they have to have some kind of data dependencies so that the compiler cannot run the other function first, because it kind of needs something as a result from the previous call. Yeah, and the way this is being done is it's suggestively called state because it resembles the state monad. But the idea is really, well, there's a pattern when you have a discussion with a lot of people, and they all talk to each other and nobody understands anything. So you introduce a token, and only the person holding the token is allowed to talk. So only one person can talk, and the token has to be somewhere, so you maintain the multiplicity. And the idea here is really the same thing. So we have this token, when we have the token, we can compute something, and then we have to pass it on. And when we have the token, that is kind of the capability of having a single side effect at a single moment. And then, as you know, we can take the state monad and, well, take the state type and make it a monad. So we have this box machine here, and we can basically just chain it one after another. And now you might imagine that the first guy here gets the token, says hello, and then loses the token, so he can't say hello again. And then the second box says world, and everything is fine, and we print hello world and not world hello. Yeah, and this is your standard state monad picture that you have here. But the problem with that is, although you could probably do it that way, it's not very efficient. Yeah, I gave a talk about this last year, but just for now, basically, the key thing that a let block does is a heap allocation. So everything you bind in a let is, a relatively expensive call to malloc because you have to find empty space and then maybe garbage collected later. So we have something we want to do, this transition here. We consume the token, we create a new token and a tuple to hold them both, and a result. Then we have to calculate the result from the previously gotten value, and then we can continue running this. So in the end, we have 4 heap allocations here. We have to create a tuple, we have to create a new token, and we have to create the value that we computed. So for example, if you take get char, for example, the token would just, well, the token is symbolic, and the character would be the value that we computed. But there's a lot of redundancy in here. I'm guessing not many people are familiar with unboxed tuples because they're a bit magical. But I hope you're familiar with boxing. So in Haskell, all values are what's called boxed. So an int is a black box that promises that once you look into it, there's going to be an int available in some way. But the black box can actually contain one of 2 different kinds of, conceptually, 2 different kinds. It can literally contain an int, or it could contain a computation that results in an int. And the way this is done in the box is, well, you have a pointer to the computation. But then every time you get a box that says, hey, I'm an int, you have to open the box and look inside and, figure out what to do. So this is what's called boxing. And you have this one layer of indirection because you have to follow the pointer and maybe calculate something. And then there's unboxing, which is, well, get rid of the box and just store the actual integer that's in the box. And that's frequently an optimization to do if you do heavy numerics or something like that. You don't always want to open and close black boxes and stuff like that, but you just want to work with the actual value. And there is a similar concept with tuples. So when you have a tuple of A and B, the way this looks like in memory is, well, it's a kind of a header field, I guess you could call it. And in there it says a couple of things like the overall size for garbage collection and how many constructors it has, and I think sometimes also the size of the fields that follow. But the point is this tuple is, first and foremost, it's a thunk. It's a black box with two fields in it. And so these are the fields back here. And each of these fields may contain, like, I don't know, if it's a tuple of char and int, it contains, well, a box of a char and a box of an int. So what you have is this indirection from the tuple, and then an indirection for each component. And these are if you look here, we have these three allocations here. We have the tuple itself, we have the tuple entry 1, and the tuple entry 2. Whereas an unboxed tuple, it's just, well, it's not really a tuple. It's just literally these two things in memory next to each other, which has a couple of advantages and disadvantages. So for example, if you look at this, it's not really a tuple. Like, there's nothing saying this is a tuple. This is just two memory cells just laying around in memory. But on the other hand, there's a way of optimizing this more, because when we know something about A and B, we might, it's just nicer to work with for a compiler at the cost that you can't really store it. So you have to immediately consume it again. And that's kind of the point behind it. So it's a way to have two values, but never having to allocate a tuple. So with that in mind, we can go back to our monad definition from earlier and change a couple of things. So in general, as I mentioned, let is a heap allocation, and the heap is comparatively slow compared to the stack. So we can transform these let bindings to case bindings, which do just the same thing, but case usually goes on the stack, except for when it doesn't, but most of the time it does. So that's one thing, and then we can make use of our unboxed tuples. So before we had case fx of tuple, which means calculate fx, then allocate a tuple, put the two values in, and then case match on it again. Whereas when we have an unboxed tuple, this f prime x, we'll just put the two values in two locations and immediately case match on it, resulting in just no allocation at all. So this case is kind of free. I mean, we pay the cost of applying f, but we don't pay the cost of having a function call. Sorry, not a function call, a tuple allocation. And when we put that into our definition, we lose a lot of allocations. So this run state transition token before, which gave us the tuple, it never allocates. It just puts its two components somewhere, and case matches on it. And we get our new token, we get a result, and we can apply our function to it and just continue. But we still have, we get a tuple allocation, or an entry allocation for our result, and another one for the new token. And of course, a heap allocation for what to do next. So in our hello world example, what to do next would be print the bird tick after saying hello world, or what is your name, I think it was. That's a bit better, but it's not good enough. So what do we really need the token for? Like, do we really have to pass on the token? Can we just say, oh, you have the token now, and people agree on it? There's no real reason to have an actual physical thing, because that's laborious to carry around. And the way GHC does this is just takes a token but completely ignores it. So we have this data type called, for some reason it's called state hash. It has nothing to do with state or anything like that. So I call it discard. It's effectively just a type that has a single parameter no constructors, so you can't really have a value of it. And it just throws the S away. So why is this useful? Well, you can still define a new kind of state transition where, given a non-existent token, you create a result, like a new non-existing token, and a resulting value. So this kind of optimizes away the need to create new tokens, because you're getting no token anyway. So it's not like you're not getting a token, but you're getting no token. It's a bit like, I don't know, if you want to go somewhere and it's free, but they still require you to make the gesture of giving them nothing. So that way, this gesture ensures that order is maintained. So there's still a dependency, but there's nothing being passed on. So if we, this should have been hashes here. So this is an unboxed tuple. Oops. Yeah, so what do we gain if we don't use the token? Well, we don't really need the tuple anymore, right? So we create this run state transition token of, then we match on the result. And we have this X here, which is our result. We have to allocate it. But this token has size 0. So there's actually a tuple consisting of something and then something of length 0. So we might as well just not allocate anything for that. So in the end, we have just a single value that we pass on. And, well, that's it. So we kind of have the same effect as if we had written f of g of h. But this imaginary token that we're passing on, that makes sure that things appear in order and exactly once. So this is just a really neat trick to bolt on a thread to follow through the program. Okay, well, so what are we doing? Well, we pass around a token. Then we optimize the token away because we don't really need it. We need the idea of a token. And then, well, what is I/O? Well, now we have ordering and everything. Now we just need primitives to work with this non-existing token. And I/O just has a special non-existing token. And I guess you guessed it already. Real world is that token. So there's a data type. It's called real world. It has a bunch of special properties that I'm not going to go into. But in the end, it's just something you discard. So it's not like we're passing on the real world. Like some people, I've seen it many times, they said, oh, in Haskell, you model the entire universe, and then you act as if you create the universe again and again. It's like multiverse theory. It's not really, no. It's just not really a good name, this real world thing, because it's always discarded. It never exists. It's never allocated. I think you could create a value of it because it's isomorphic to unit, but don't quote me on this. But it's not the point. So it's always discarded. It never exists because it's always discarded. So I/O is really a new type from a discarded real world onto an unboxed tuple, of, a value and another discarded real world. And when you look at this file here, GHC libraries HS, then you will see this monad I/O instance is really just the state monad instance, but with special magic bolted onto it. And you may even wonder why I put this hash behind the discard here. So, well, in GHC it's called state hash, and it has the special property that is size 0. That's basically a little magic to, save memory, and it's an optimization. And you've also heard of the ST monad, I'm guessing. So that's like a close relative to I/O, which you can use to create mutable updates and then encapsulate that in a way so that from the outside, there's a guarantee that you cannot see the mutable updates. So for example, if you want to sort a vector, you don't want to do the functional thing of flipping two elements by creating a new vector and then copying and copying and copying every time. But you can use ST, where you just do the mutable updates and just in place modify the vector. In the end, it's called freezing. You freeze it, so then it's immutable again. And that's what the ST monad does. So ST is called, ST stands for state thread. So it's basically a way to thread the state of the real world or S through the program. And then I/O is a specialization of ST where the state parameter is not left open, but it's specialized to real world. I don't think these two are type synonyms in GHC right now, but the implementation is basically copy-paste. And these are the only two useful ways of using this discarding pattern. Either you leave S completely open, and that in the end, when you run an ST computation, you require that this S is completely unspecialized, so it cannot be int, for example. So you cannot leak state out because there's no value of type S. And then you get the guarantee that you cannot observe side effects from the outside, or you do it in a way that I/O does it, and you put in the real-world token, but you give the user no way to really create the real-world thing. And the only way to do this is actually the main function does it, which I'm going to go into now. So, well, we now have this I/O real-world thing, but to start this process, we need this non-existing token in the first place. So how do we make something up that doesn't exist, really? Well, it's the same way if you have a function that's called crypt. It takes a string and also takes a void argument. And void is a type that has no values, so you cannot really make a value of it to give to crypt. But you see, crypt just ignores this key of type void. And now we have a value created with this crypt. We want to get the hello out, but in order to get the hello out, we have to apply crypt, and we have no value to put in here because void has no value. So, well, what do? Well, we just cheat. I mean, Haskell lets us do this. We can just make up values of arbitrary type. So if we find some way to just create something that doesn't really exist, but we're not going to actually need it, we're fine. So what's the secret? That's just, give us hello because the undefined is never evaluated because of laziness and the key is unused. Yeah, and there are two main ways. Well, there's one main way and one other dirty, dark way to make up a real world. Main is, well, the runtime does it. So when you enter the program, the runtime kind of jumps to the main value. And it also gives it a symbolic real world. Or it basically pushes it and starts now get going. So there's a primitive that is responsible for doing that. And then there's the other good infamous friend of ours, which is called Unsafe_perform_IO, which is a function that shouldn't really exist, but we need it sometimes, so it does. And Unsafe_perform_IO also just uses an unsafe or a primitive that just says, well, you can't do this, but just do it anyway. So with that in mind, we can look at probably the simplest of the unsafe functions, which is called Unsafe_dupable_perform_IO, which is a close relative to Unsafe_perform_IO. It's a bit simpler. So we have an I/O action. This action, given a token, will, compute a value and give us a new token. But, well, we don't have a value, but luckily we have this run RW hash, and whenever anything includes a hash, it's probably from deep within the bowels of GHC. So it's, depending on where you use it, it has names like magic hash, or people call it evil hash, and unbox tuples are also a bit, well, not really useful for everyday programming, but sometimes you kind of need them, so they're there. So this will just make up a real world to give to act, and it just creates a new token, wherever that is from, and ignores the token and just gives you the resulting value. So this allows you to take an IOA and make an A out of this. So given the recipe to make a cake, this makes you a cake. Well, this doesn't really make you a cake. This just takes the recipe and poof, it's a cake. Needless to say, this function is, well, it's unsafe, but it's also one of the unsafer ones, and probably shouldn't be used all that much. But for high efficiency computing, like sometimes in byte string, for example, they use a lot of these things. Or when you work with the FFI, I think Neil used it in his talk earlier. Like he had some C functions and he combined them in a way so he was sure that they don't have side effects, so it was safe to put Unsafe_perform_IO around it. And then the burden is on the programmer to make it not, do silly things. Yeah, now that we can chain and run these things, all we need is just primitive functions that make use of this. And well, there's no real way to make up all these things, so they have to be primitive. So in the end, there's probably the most important function in low-level Haskell, which is called ccall. And that just places a syscall to a C function and does it. So this put char here, actually this ccall put char should be regarded as a primitive that takes a char argument and just makes a proper Linux syscall to print a single character to the terminal. And then it just returns nothing. And likewise, there's, for example, fork.io, which is a bit more explicit. It takes a state token, then runs fork hash, which instructs the runtime to create a new fork or a new thread. That gives it a new token and a thread ID. It returns wraps the thread ID, and that's it. And the ... is exception stuff, which I'm not going to go into. But yeah, there's a bit more to this than I'm going to explain here. But in the end, you will see it all boils down eventually to having these very low-level fork hash things. And these actually, when you run them, they do have side effects. So this, at some level, becomes like when you print in Scheme, for example. So when you evaluate that part, you get the side effect. But this is very far away from Haskell already. So as a programmer, you don't have to care about this. And the compiler just does it secretly in the background in a way that doesn't compromise the purity of the language. So coming back to the talk I had with Duncan, he explained all the unsafe functions to me, and it was really enlightening. And anyway, it started off with, well, let's start with the safest one, which is unsafe perform IO. So this one is relatively safe, his words. He's probably right. So I mean, what can you do wrong with unsafe perform IO? Well, GHC is free to reevaluate things. So if you unsafe perform IO print, for example, it may run 10 times or 100 times or an infinite amount of times maybe. But it doesn't write into a different memory region and segfault your program. It may write twice to a database or delete twice, but it's not terribly bad. So it could be much worse. Relatively safe. Then there's unsafe dupable perform IO. This one is relatively safe. And there's a reason I wrote it like this. So what unsafe perform IO does, it makes sure that when you have a thunk that contains it, there is kind of a mutex, so that when you're in a concurrent scenario, only one evaluation can happen within the unsafe perform IO at the same time. So for example, if you call to C and the C function just calculates the sign of a value, then that's safe to do with 2 threads. But when the C function, for example, prints, it would be a bad thing to go in there twice, because it would print twice. So unsafe perform IO says, well, this thunk can only be evaluated once at a time. So it just has an implicit mutex. And you guessed it, unsafe dupable perform IO does not have that mutex. So when you say print relatively safe, it might be that the GHC runtime just it feels like it and just says, oh, this is a pure function. Obviously, it says it has type A, not IOA. I'm going to evaluate this 5 times. And it's going to print 2 T's and 3 Y's and 2 S's and, So it still kind of does the same thing, but may do it in a weird way in multiple times. So this is, I don't know, probably not safe anymore. And then there's our good friend inline perform IO, which is just completely messed up to the point where it has a synonym in byte string called, I think, accursed unutterable unsafe perform IO. The reason for this is unsafe perform IO and unsafe dupable perform IO, they still have this form of a function where they take a token and make something out of it. So in order to do anything there, they have to follow the semantics of a function application, and the compiler cannot really inspect the function, because in order to inspect the function, you have to apply it to something. Inline perform IO does not suffer from this problem, so the compiler can actually look inside the body of the function. So for example, there was a bug in byte string. When you created a byte string, it would allocate a buffer of length 1, also 1 byte. And GHC was, oh, I can do common sub-expression elimination here. So it would take all the single length byte strings and just put them into a single variable. leading to all byte strings of length 1 to alias each other, which is pretty bad, and I'm guessing it's really hard to debug. You should probably later Google accursed perform IO something. You will probably find a place in byte string. It has a block of this much above it. It says, I don't know, flee, you're opening the gates to hell, run, and don't use this function. And then there's a list of tickets that should scare you away. And these tickets are really brutal, low-level stuff where things just broke because of inline perform IO. But of course, the benefit might be that when you're really sure that this is a good idea to use, it may be beneficial for performance. But I've never needed unsafe duper perform IO. I don't think I will ever need that one. I certainly hope so. So yeah, this is the hierarchy of unsafety. I'm guessing stick to 1 or maybe stick to 0, which is don't use them. But sometimes when you use the FFI or for debug.trace, for example, it uses unsafe perform IO to just do dirty work. But so the reason we have unsafe perform IO at all is because of the FFI. Because when you interface with C, you can never be sure whether there's a side effect involved. So when you are, as a programmer, sure, then you can use unsafe perform IO to erase the IO. But the compiler will not help you. And yeah, so sometimes it's safe. Most of the time, it's not. So concluding, this is I'm hoping this was kind of an anticlimax because there's nothing really special happening. It's mostly an optimization of juggling around unsafe primitives in a way that you don't notice in the end. It's really just a magic trick, I guess. So we order computations via the token. Because we don't really need the token, we discard it. When we need a token, we make up one and then discard it. So the real world never really exists because the real world would probably take too much memory to store in a Haskell program in order to print. And in the end, the STG, which is the machine that runs Haskell, is given a certain set of primitives. And when it reaches them, it just doesn't care about purity. It just does the side effect. And yeah, if you're implementing something, cheating is a valid strategy. Like, why not do it as long as it's hidden? So yeah, not sure what to take away from number 5, but you'll have to find your own ways to use these functions, and yeah, maybe one day you'll find something that use it. Yeah, well, thank you, and I'm gonna leave you with something relatively safe that you can do with unsafe perform IO, so it's not really all that safe.
Okay, does anybody have any questions?
Just out of curiosity, what does C-call actually returns? Because there we discarded it and returned unit. But is there anything useful we can do with it?
I don't know what it returns. So it's a hardwired primitive. It might just return A, like undefined, so you can use it whenever you want. I'm not sure. So I don't think there's a file that says C-call. I mean, the argument of C-call is part of the C-call already. So it's not really a C-call function, but C-call put char can be regarded as a primitive, so you can't, it's not really something you can parameterize over. So I guess the answer is it's deeply hardwired, and I don't know.
Okay, thanks.
But I mean, you can just use any C function there. Yep. Probably also malloc and stuff like that, yeah.
Do we have any more questions? No. All right, well, thank you very much, Guchen.